Welcome back to the next lecture on weak convergence of measures on metric spaces now. Last lecture, we recalled or defined many concepts in topology. This lecture, everything is only for metric spaces. Let me recall. The ultimate target is to prove convergence of random walks to the Brownian motion and also to prove the central limit theorem on the way. So we need to prove in some abstract sense convergence of abstract random variables. And we're going to do the same that we did in Stochastic Ions for convergence of distributions. But now distributions are more general measures. In Stochastic Ions, the distribution of a random variable was a probability measure on the real numbers. Now, in this section, we're going to discuss convergence of measures on just some metric spaces. The sigma algebra is always going to be the sigma algebra of choice. So let's define the convergence just in the same way we did in Stochastic Ions. It's just a little bit more abstract now, because in Stochastic Ions we had convergence of expectations, if you remember, in the definition of convergence in distribution. But those are, of course, integrals, f against laws, integral f gp x. Oh, cannot read it, but you know what I mean. So now we do exactly the same, but in a general setting with no random variables, but the random variables with values in the metric space are going to appear later. So here's the definition. Fix a metric space, E. Fix the Boole sigma algebra generated by the open sets of the metric, and take a sequence of finite measures. Most of the time, we're going to speak about measures which have mass 1, probability measures, but let's first define it a little bit more generally for finite measures. We say that sequence converges weakly. Now we call it not convergence in distribution, but weak convergence. So we say it converges weakly if all integrals converge for bounded continuous functions. Recall, bounded continuous functions are important because they are separating for the set of finite measures. So as I recalled, this is in Stochastic Ions, the notion of convergence in distribution, if we just fix the real numbers. There are different notions. So sometimes, or in this lecture, we are mostly going to use this notation with W for weak. Sometimes we also write this notion, but often you can also see the notion with a double arrow. So if you see this, and this means this is a sequence that converges weakly to the limit measure mu. Let's start with some remarks, and then we are going to prove two theorems today. One you already know from Stochastic Ions, just a more general setting, and the other one looks a little bit weird. It's characterizations of weak convergence in different terms. So first, a small warning. For those of you who attended function analysis, this reminds you of weak convergence. Actually, it's not weak convergence. So this is not the weak convergence you got to know in function analysis. This is the weak star convergence in function analysis. And if you've not attended function analysis, don't worry about this. But for those who did, the reason is the measures are the dual space for the continuous bounded functions. And then you check the definition of weak star convergence, it gives you exactly this. And the notion of weak star convergence, you always needed to test the sequence against the dual space. So this gives you exactly this. So the notion weak does not come from weak convergence in function analysis. The notion weak comes from a different reason. The notion weaks just comes from the fact that this is just a very weak concept. So if you remember convergence in analysis 2, we discussed that stronger norms or stronger metrics define stronger convergence. Go back to analysis 2 if you forgot this. And this is the weak in the notion, weak convergence emphasizes that this is quite a weak notion of convergence. So many sequences converge in weak convergence, and we can write down different notions of convergence on measures, and then less convergences, usually. Less sequences are going to converge, so the convergence is stronger in the sense of strong and weak from analysis 2. So weak convergence is a quite weak concept of convergence. We can often prove it, but we are not going to get a lot from this. Just recall stochastic ions, for instance. Weak convergence here is the same as convergence in distribution in stochastic ions. Convergence in distribution is, remember that picture with all these arrows, is the weakest of the modes of convergence. So the least preferable convergence mode in stochastic ions. It's a weak concept. That's why it's called. Okay, here's an important remark. We're still thinking of putting this as an exercise, but it might be a little bit too complicated, but it's not very complicated. There are just quite a lot of things to check. The claim here is that this convergence, which was just defined this way, is actually the convergence of a metric. So that convergence is metrizable. So there's a metric which is called the Powerhoof metric. It's defined like this. You take two measures and then you compare the two measures by enlarging sets. So you take a set B and then the epsilon enlargement, which we're going to need later again, is just all the points added to B which have distance at most epsilon. So now you compare the enlargement of the set, you compare on these two measures, and this defines a metric. So if we do it as an exercise, you first need to check this is a metric. And then you need to check that a sequence converges in the sense just defined above, if and only if the metric on the distance of a sequence from the limiting point goes to 0. So actually, we are not going to use it anywhere. That's why it's not so important if we don't prove this. What you should keep in mind, this definition, which is not a metric convergence definition, it's just somehow defined. This is really the convergence of a metric. And as an example, we know that limit points are unique. So if you have a sequence that converges to some measure mu, and it also converges to some measure nu, then they are the same. Because this is always true for convergence in metric spaces. That's one remark. The other remark, and that's deeper, the other remark is, if E is a nice space, say a Polish space, so we have a metric space and we want it to be a Polish metric space, so complete and separable, then the same is true for the measures. Okay, now it's very abstract. Measures are already abstract. Well, sure. Now we have convergence of measures, which are measures on some metric space, and this is again a metric space. Perhaps just a small word why that might be of interest. People study processes whose values are measures. So they are called measure-valued processes. Sometimes they are called super processes. So if you learn about processes with values in topological spaces, in metric spaces, in Polish spaces, as we do in this lecture, then this statement tells you that you can also study easily, not easily, but with our techniques, processes whose values are measures. So why is this interesting? Measures, as we discussed a lot in stochastic ions, essentially explain the distribution of mass. So let's think about R2, and then think about distribution of mass as something like this. So now a process with values in the measures is going to be a process where over time the distribution of the mass is just evolving. So if you want to model something like this, you have a cloud and you want to see how the cloud evolves in time, then the right concept is to study a process whose measures are, whose values are measures. And that's these measure valued processes. And in order to develop that theory, it's useful to know that the values this process takes are from the Polish space. And that's why it's useful to know the measures are Polish space. So this is actually the reason why in the book of Klenke, there's a lot of emphasis on the convergence of infinite measures also. Because Klenke himself, he works a lot on super processes. I also have a paper with him on that topic, where we do exactly this, but the measures are infinite. So for that study of measure valued processes, it's very useful to have all the theory also for infinite measures. We are not doing this here. So if you check Klenke's book, the proofs are always much, much longer and much harder. You need so-called radon measures if you want to talk about the same story in infinite measure, for infinite measures. So we don't need this for the lecture, so we skip it, and either measures are finite or have mass 1. Okay, last final remark. The function which is constant 1 is, of course, here bounded and continuous. So the total mass of the measures, which is the integral against the 1 function, converges. So in particular, if I have a sequence of probability measures, so the integral against the 1 function is 1, then the same is of course true for the limit, because the limit is here just the limit of the constant 1 function. So the message is just, if we have a sequence of finite measures which are probability measures, and they converge weakly, then the limit is also a probability measure. So we are not losing mass, or we are not gaining mass in the limit. So in other words, the subset of probability measures is a closed subset of the finite measures. Closed in the sense of the topology induced by the Powerhoof metric. Okay, here's a small example. If you take the sequence of Dirac measures in 1 dimension, that only takes mass on 1 over n, so we have that sequence, and then this sequence converges weakly to the Dirac measure at 0. But let's just check it. It's a very simple example. So what do we need to check? We need to check, there's an n missing. We need to check convergence of this integral towards this integral for all bounded and continuous f. So let's take a bounded and continuous f. What is the integral of a function against a Dirac measure? Well, it's just the function at the point of the Dirac measure. So it's f of 1 over n. Since we assumed f to be continuous, this converges to f of 0, which is the integral of f against the Dirac measure at 0. And that's the definition of weak convergence. Okay, as I mentioned above, we are also still looking if we find a nice exercise for this, but they tend to be complicated very quickly. There are many other ways of defining convergence of measures. And nobody's telling us we need to do this. There are other metrics on measures. There are other ways of defining convergence without metric. Usually they are stronger. So less sequences converge. And that's, I'll say it again, motivates the wording weak convergence. So very often, either the other notions compare the measures on sets. So your first idea might be, how about the notation to say I have convergence if this converges for all, there's no n here, for all A? Well, that might be an idea to do this. And that leads you something similar in this direction to total variation convergence. Or you might take other functions f. And the next big theorem is shedding some light on this. It's shedding some light how we can relate these weak convergence notions that we defined to convergence of measures of sets and other integrals. The theorem is called Portmanteau. Portmanteau is called Kleiderständer oder Kleiderbügel in French. So it just means there are many different statements lined up on this portmanteau. So, but you should please keep in mind, it just gives equivalent notions of weak convergence. One is with different class of function, and the other more useful ones are about, well, what about convergence of sets, sets of measures? That might be the first idea you would have to define convergence of measures. So here are the equivalent statements. So we have a metric space. We have a sequence of tension, probability measures here. There's a similar statement for finite measures, but it looks less handy. So I decided to only put it for probability measures, even though the proof is the same. So now the following are equivalent. We have our weak convergence. Now the first equivalence is perhaps not surprising, given we know these different classes of separating functions. We have convergence of these integrals for bounded Lipschitz f. So this looks more simple because there are less Lipschitz functions than continuous bounded functions. Yeah. Lipschitz is always continuous, but continuous is not Lipschitz in general. So now we come to convergence of sets. So let's perhaps start with the fifth. So this is what it looks to be the most useful one. It tells us the measures converge tested on sets for all sets, but unfortunately not all sets, but only the sets for which the limit measure has measure 0 on the boundary of the set. So that looks quite good. Without this one, this would be something very useful, but that's not weak convergence. That's too many sets. We only take the sets with boundary 0. Unfortunately, this looks more useful than you believe. The reason why this is not very useful is, or in many situations not useful, you need to know the limit measure. But you need to know quite a lot about the limit measure. If you have a sequence that converges to some limit measure, which you don't know very well, and in particular, you don't know for which sets the boundary has measure 0, well, then you cannot do anything with it because you don't know what sets to check. So that's the drawback. The drawback is the limit measure appears here. It would be easier or much more useful if the statement here would not involve mu. So for instance, something like for all A with countable boundary, or something that only depends on the set. But since this is only dependent on the set, but also on the limit measure, it's sometimes hard to check. But in proofs of this lecture, this is used and it's useful, but in practice, in many cases, this is a drawback that makes it hard. So now here are two weaker versions, but not weaker, they're equivalent, but they look weaker. So the first one is a statement that actually we only need to check closed sets. And the other one is we only need to check open sets. And even more, we only need weaker statements. We need the lim sub of the sequence is smaller or equal to f for all closed, or the lim inf of the sequence of sets is larger or equal to the limit of the set for all open sets. But keep in mind, but that's not equivalent, if you knew the limit of all open or all closed sets is equal to your measure, then of course this also holds. If the limit exists, then the limit is the same as lim inf and same as lim sub. And if it's equal, then of course it's also small equal to. Yeah, so this is not equivalent. This is stronger. If you have convergence here for all open sets or for all closed sets, then these two tell you you also have the weak convergence. Okay, so as I motivated before, this one is about different notions of convergence in integrals, and all these are about convergences of sets. Okay, there is 6 very, very important equivalents, which we are going to prove in the next lecture. And the 6 equivalents only holds in a Polish space is called Powerhoof Theorem. That equivalence is telling us weak convergence, also equivalent to convergence on even less functions. Here we know in the definition bounded continuous. Here we proved Lipschitz, but you actually only need some separating family plus something which we call tightness, and we first need to define. So keep this in mind. There's a bunch of different characterizations of weak convergence, and all of them are used. So this one turns out to be the important characterization in order to speak about characteristic functions and the central limit theorem and the convergence of random walk to the Brownian motion. Right, so let's first start to prove Portmanteau Theorem. So first equivalence, or first implication is trivial, because this assumes convergence for all bounded continuous, while these ones are bounded and Lipschitz is continuous. So that's clear. Okay, now let's do this one. 2 implies 3. So what do we need? We need to fix a closed set and prove this inequality. Okay, let's take a closed set. And you might not be too surprised so much. This one is a convergence of integral, and this is also an integral. Yeah, keep this in mind from separating classes last time. This is the same as the integral of the indicator of f d mu n. And we know convergence of Lipschitz functions, and now we want convergence of something that we know how to approximate with Lipschitz functions. You have that picture in mind, I hope. So we are using the same again. So we have our f, and now with the functions from last time, we approximate the set f by the indicator, which is 1 on f, then smooth down in a Lipschitz way to 0, and outside of the epsilon enlargement of f, it's 0. This was our function. This function, sequence of functions, is bounded by 1, so we can use dominated convergence. It converges pointwise to the indicator because the set is closed. So here we use the closeness of the set. If you ask yourself, why do I need open and closed stuff? Here, that's why we need it. It's closed. Okay, and now we just need to do the right things with dominated convergence and lim sub and stuff. It's only a few lines. So using this, first, as I said, this one is an integral over the indicator. So by monotonicity of integrals and monotonicity of that function, so this function dominates the indicator of f, we know the lim sub of the measures is smaller or equal to the lim sub of those integrals. Okay, so now we only need to deal with those. But we are almost done. So why? So we have this inequality for all epsilon. Yeah, this is true for all epsilon, if it's like this, or like this. So I can also take the infimum over all epsilon, if it's true over all epsilon. Okay, so the lim sub is smaller or equal to the lim sub of those guys over epsilon. So now important point, this is a Lipschitz function, as we discussed or you did on the exercises. So the limit exists by assumption. We assume that limit exists. And that's the assumption 2, which we are using. So lim sub is the same as the limit. And we also know what the limit is. The limit is that integral, but mu n replaced by mu. Okay, so that's it. So, and what about this one? Now, well, we have an infimum over these guys. But also here, from dominated convergence, we know that this guy, if epsilon goes to 0, converges to the integral with the function f replaced by the indicator. That's what we used last time in the separation. And this gives mu of f. If we have a sequence that converges and it's decreasing, then the limit is the same as the infimum. So what do we have? Mu of f. And here we have lim sub of mu n of f, and that's exactly the statement. So closed sets, measures of closed sets are integrals of indicators of those closed sets, and closed set indicators, we always deal with this function, sequence of functions. So that's 3. 3 and 4 equivalent is just writing mu of f for open, or f complement, as 1 minus mu of f. If f was closed, f is open, or the other way around. So this minus turns lim inf into lim sub, and smaller equal to larger equal to. That's why 3 and 4 are immediately equivalent. And here you see where things are a little bit more tedious if you replace probability measures by finite measures. Because in that case, I also have, so if I have a sequence here, mu n of the entire space minus the complement. So I also need to deal with this sequence, which is not necessarily constant if I have a sequence of finite measures. And I just wanted to remove those statements about this to have it clearer. So next, 3 and 4 implies 5. 3 and 4 are equivalent. So if I assume 4, I can also assume 3 or both of them at the same time. So what do we need? We need a measurable set with 0 boundary. And now the proof is very simple. So let's start perhaps at the end. So we just use the following simple observation. The boundary is the disjoint union of the interior and, no, not the boundary, the closure, sorry. The closure is the disjoint union of the interior and the boundary. So we know the measure of the closure is the measure of the interior plus the boundary. So if the measure of the boundary is 0, as we do by assumption, we know the measure of the boundary and the measure of the interior are the same. And now we can finish the proof by just using monotonicity of those measures. So we have estimates for the lim sub and an estimate for the lim inf. So what we are going to show is that the lim sub is smaller or equal to the lim inf. But since always the lim inf is smaller or equal to the lim sub, this implies both are the same. But if both are the same, then they are equal to the limit. And if the limit has the estimates 3 and 4, then the limit is just equal to the measure. So we show the lim sub is smaller or equal to the lim inf. Okay, what do we do with the lim sub? So we use monotonicity of measures by increasing A, enlarging A to the closure here. So it makes it larger. So now we use that assumption 3 for closed sets. This is closed, so it's smaller or equal to the measure of the closure. The lim sub smaller or equal to the limit for closed sets. So now this is the same as the open set. The measures of these two are the same, like this. So now I use, this is 4 here, to say, well, that is open, so this is smaller or equal to the lim inf of that sequence of open sets. And now I do the same as before. I use monotonicity. The interior is a subset of A. So measures have monotonicity. So the lim inf of that sequence, mu n of A, is larger. And now I have this is smaller or equal to this. That's it. Okay, so this combines beautifully measure theory, monotonicity of measures, and topology, open sets, closure, interior, closed sets. Very nice. Okay, so these are the simple directions. The proof is only long because there are many statements. Now there are two little bit more complicated statements. So this is 5 implies 3, and then we have to prove the last final one. Okay, what is 5 implies 3? Let's check. So the convergence of these ones implies the lim sub stuff. So how do we argue? So we take a closed set for which we need to discuss the lim sub. Now we enlarge the closed set by delta. Yeah, so if you have a closed set F, then we make it a little bit larger by including all the points with distance at most epsilon to the set. That's what we call F delta. And now here's a small but crucial observation. So we have that set F and we enlarge it. And the claim is the boundary of the enlargement is contained in the points which have this distance exactly delta. These sets must not be the same, but it's a subset. So why is this? So what are the points in the boundary of this enlargement? Well, points in the boundary are those points for which there's a sequence converging to the point from the outside, and there's a sequence converging to the points from the inside. So that's one of the many equivalent notions of the boundary, which we discuss in analysis 2, since here we're in a metric space. So, but what about these ones? These are the points, by definition of F delta, which have distance to F strictly larger than delta. These are the points, by the definition of F delta, which have distance smaller or equal to delta. So now the distance is a continuous function. So if we have a limit here, then it's this limit, so the limit of those ones. So the distance of the point to the set is smaller, is larger or equal to delta, because they are all of distance larger than delta. In a limit, strictly larger becomes larger or equal to. Same from here, all these have distance smaller or equal to delta, so the limit has a distance smaller or equal to delta. So now taking both together, if I have that point, then the distance is larger or equal and smaller or equal to delta, so it's equal to delta. So that's why it's in here. Okay, so now we combine this topological argument with measure. So these sets are now disjoint. If I have a point, it cannot be in several of those because the distance is just a number. So they're disjoint if I change delta. Okay. Well, they are of course measurable sets because they are boundaries. Boundaries are closed sets and closed sets are measurable. So now the point is, and I think we should have put this as an exercise on the first exercise sheet of Stochastic Ions, perhaps next year. If I have a measure, there cannot be uncountably many disjoint events with strictly positive measure. Play around with this Stochastic Ions exercise, essentially. And of course, the problem is subadditivity. You need to construct a contradiction, Widerspruch, using the countable additivity of measures. That's essentially the problem why a uniform distribution on an interval is not so easy. So what does it mean? I have uncountably many of these measurable sets which are disjoint. So only countably many of them can have a finite measure, a positive measure. Okay, so there is a sequence of deltas that goes to 0 for which the measure of these boundaries is 0. So let's call the sequence delta k and note that for this particular sequence, the measure of these boundaries is 0. So, but now we have sets for which the assumption of 5 applies. These are sets for which mu has a measure 0 on the boundary. So for those guys, we know the limits of mu n of f are mu of f. So we can use this to finish the proof. So we apply 5 to f delta k, but actually we're interested in f. So somehow we need to do something with f and with this sequence. And the point is now the following. we take the lim sub of mu n of f. We don't know this converges. We only know from 5 the limit of mu n of f delta k converges. So, but we don't know it converges, so we take the lim sub. Now we use monotonicity of measures. F delta k is an enlargement. So we have here the monotonicity. We have the lim sub of that sequence. But this is a sequence of measures which with a sequence of measures of a set with boundary 0. So here we know convergence. So limit is the same as lim sub. And the limit we also know is the limit measure of that set. So we see the lim sub of mu n of f is smaller or equal to mu of f delta k. Problem is we don't want to have a delta k, we want to have an f here. But left-hand side is independent of k. So we can do this for every k. So we can do it here. So if we like, we take limits here. And now we have monotonicity of, not monotonicity, continuity of measures, because these f delta k's are decreasing, and they are decreasing to f. So this is monotonicity of measures, that right-hand side converges to mu of f, but since all of those are larger or equal to that lim sub, also the limit mu of f is larger or equal to. And that's it. That's what we wanted to prove. Final step. So, and this is the most complicated one because a new idea appears. An idea which is confusing us because we know it in a simpler fashion. So we want to prove that this inequality of measures in that lim sub implies convergence of integrals. So this looks strange because integral measures, we don't know. So the trick is, as always, we want to write the integral as a sum. So the integral is a sum of measures with some weights if this is, if f is an indicator function or f is a simple function. So we want to approximate our function f by simple functions. And now I recall for you the main idea of measurable functions from stochastic ions, how those relate to simple functions. Recall, measurable functions are exactly the function you can approximate with simple functions. So what did we do? There was a colorful picture. So we divided the image space, the real numbers, in intervals. And then we checked the pre-images of our given function on these partitions of the image space. And on the pre-images, we gave the value of the function the smaller value. So then it looked something like this. Like this. So this was the way to approximate measurable function by simple functions. Yeah, here, that's the main point. We divide the image space into these partitions. And these partitions, they had the form something like 1 k divided by 2 to the n to k plus 1 divided 2 to the n. And here, 1 open, 1 closed. And we needed 1 open, 1 closed for not double counting. Because otherwise, values could be in both of those indicators. So the values of the function could be in 2 of those if they overlap. So that's why we had 1 open, 1 closed. So now here comes the trouble. This is not a closed set. Our assumption is something on closed sets. This is neither open nor closed. And here's where the trouble comes. So this is what we would like to do, approximate the integral by a sum. Then in the sum, we have all the measures of these pre-images of those sets. For those, we can apply the assumption on that limits of closed sets. Well, but they are not closed. So that's why the argument goes very similarly. So we have an integral which we write with a sum that looks similar to what we usually do, but there are 2 sets. So the idea is now the following. We again take the image space, but we split it into these closed sets. Well, now the trouble is I have double counting. If I take a point here, then the point is in this one, but it's only also in this one. But so everything I will do only up to 1. So I'm going to use all these closed sets. Now they're closed, but I have double counting. And then I have to deal with the double counting. So this is a version of that most important construction in stochastic ions for measurable functions using closed sets. Okay, that's almost all you need to know. And now we write it down. So we start with some function f. So the first point is to say, without loss of generality, ohne Einschränkung, to assume our function takes values in 0, 1. So if I have some function, f is bounded and continuous, then first I add a constant to shift it upwards. Now it's a non-negative function. And then I multiply it with 1 over the supremum. It's bounded function. So, and then I just taking that function, multiplying it with 1 over the supremum, makes it a function which is scaled down and is smaller than 1. So that's why I consider f bar. But since we are interested in integrals over probability measures, all these constants don't matter. So if I can show convergence for f bar, I get convergence for f also, just by taking these constants out. So now I do what I just mentioned. So we have a function with values only between 0 and 1. And now I do that. I take these values, and instead of taking the disjoint partition of the image space, I only take these intervals, which we call fik. These are the values these are the pre-images of these sets 1 over k to 1. Okay. So now we take our function, this function here, for some f in continuous bounded, and the measure mu. And now we are going to rewrite that measure just in the form, that integral just in the form as we usually do. So usually it looks like this without this term, and these ones are just the values between two values. So now we do double counting, and it gives this one. And this gives this one. So essentially, please draw a picture and you see what's going on. So subtracting this just means I have once this, and subtracting essentially gives everything in between. So yes, I think the best is you just draw a picture for yourself as you did in Stochastic Ions, just in order to make it sure for yourself that this works. This is just saying we take the function and we always take the value above, and this just means we take the value below. And that's why one is larger and one is smaller. And this is the double counting. So this is an estimate using sums. In Stochastic Ions, we were always interested in the values below, because we always wanted to approximate by increasing sequences integrals, or not integrals, but the continuous, the measurable functions. But if I have approximations of measurable functions by monotonicity, I also get this inequality for integrals. So now, if we have this, what is this giving? Well, this looks more complicated than it is. If you write it down, I did it here, do it yourself, just write out that the sum gives you the following. You plug in the first, you get the factor 1 over k. Now you get the measure of the zeros minus the measure of the first. For the second summand, you have 2 over k, and now it's a measure of the first and then minus the zeros, and so on and so on. So it's like a telescopic sum, but not quite, because you have different constants here. The main point is, you always have, if you cancel out the first and the first, the second and the second, and so on, but if you take the difference, they don't cancel out, but they almost cancel out, because you always have I over k, and here I minus 1 over k. So I over k minus I minus 1 over k is always 1 over k. Here, for the first, we see we have the measure for the first times 2 over k, measure of the first times 1 over k. So it's 1 over k. So they all cancel out in the sense that this sum with cancellation of the double counting is just the same as 1 over k. You always have 1 over k in the cancellation, and then each of them once. And in this argument, we use that the very last summand goes away. So for the very last summand, you get fkk, and this is 0. It's the empty set. The measure of this is 0 because fkk means f bar is larger or equal to 1, but by construction, it's smaller than 1. Okay, same here. Where are we? Sorry. Same on the left-hand side. We have the same kind of cancellation, just everything, well, just plug it in. It's exactly the same. Yeah, the summand always goes 1 up, so it's always over k with 1 bigger, and they just cancel. So we have these estimates. Yeah, it's like the one, it's the same approximation as in Stochastic Ions, but there are these 1 over k things instead of I over k. Okay, so if we have this, we are essentially done. Why? Because we want to take a limit in here. And if we take a limit in here, then we have limits of measures of closed sets. And measures of closed sets, this is the assumption, they converge. Okay, let's write it down. So let's first study the lim sub of that sequence of integrals. Up to now, we don't know that sequence converges, so we cannot take the limit. That's where we take the lim sub. So let's take the lim sub. So using 2, we can increase it by taking that sum. Okay. So now analysis 1, the lim sub is getting larger. The lim sub of a sum is smaller or equal to the sum of the lim subs. So we have this. Yeah, it's a finite sequence. By assumption now, all these are closed sets. So the lim sub of these guys is smaller or equal to the limit measure mu of those closed sets. This is our assumption. So next, we take the first summand out. The first summand, well, this is a probability measure. It's smaller or equal to 1. So we estimate the first one with 1. So it's 1 over k. And then we have all the other ones. So now the small detail up here, the left-hand side, the smaller of these sums starts at 1, the right-hand side at 0. So now we have it at 1, so we have the left-hand side. So, but the left-hand side has the upper bound, the integral, so we have 1 over k from here and the integral from here. So what do we find? We find the lim sub of these integrals is smaller or equal to the integral with the limit mu. Yeah, here's the sequence, here's the limit, plus 1 over k. But since k was arbitrary, now we can send k to 0, we obtain the lim sub of the integrals smaller or equal to the lim sub of f. Okay, wonderful. So now we can ignore the bar. Yeah, if this holds for the bar, it also holds if I add the constant a and if I multiply with a constant b, yeah, since the constant b is non-negative. So I get it for f. So what I have is I have lim sub is smaller or equal to lim bar. And what did I want to prove? Oh, I wanted to prove equality. But now it's a trick. It's the same trick that you've learned in the proof of Fatou's lemma. We do exactly the same now for the function minus f. Now we didn't assume f was positive before. So we do the same for the function minus f. Well, if you plug in here, we have this one, or here, we have take this one for the function minus f. Then you take the minus outside here and minus outside here. Lim sub of minus gives minus of the lim inf. Then you multiply minus and minus. So you have lim inf here, you have the sequence here, but multiplying with minus gives you the other inequality. So you have this one. Now both inequalities are joined. Give the equality in the limit that we wanted to prove. So the proof was a bit lengthy, mostly because there were many steps to prove. Only the last step was complicated, and the trick is really to do what we did in stochastic ions, but now for closed sets. So we're going to finish this lecture with the continuous mapping theorem. Continuous mapping theorem can be formulated as follows. I first formulate it in a simpler way, and then what is written here. The simple formulation, and that's why it's called continuous mapping theorem, is as follows. Suppose we have two metric spaces and a sequence of measures on the first. Next, we have a continuous mapping phi. Then the claim is, if the sequence of measures on the first space converges, then also the sequence of the push forwards converges in the second space. We call stochastic ions. We have two measurable spaces. In stochastic ions, we usually call them omega 1 and omega 2. Now they're called E1 and E2, and the sigma algebras are the Bohr sigma algebras. There's a mapping phi in between. Oh, the tablet is a bit slow. Push forward was a measure mu here, pushed forward to the measure mu phi, or written as mu phi. Oh, that doesn't work well. But I hope you remember the notion. Either mu with a subscript phi or mu circle phi. So this was push forward. And the claim is just convergence here implies convergence here, if phi is continuous. The version here is a bit more general. We actually don't need continuity. It's a little bit like in a Portmanteau Theorem. What we need is almost sure continuity of phi in the, with respect to the limiting measure mu. So this property here replaces the continuity. So if phi is continuous everywhere, this is the empty set, so the measure is 0 and it's true. But if phi is just occasionally discontinuous, then it still works. I recall from the discussion of Portmanteau, this can be quite unpleasant depending on how well I know mu. I need to check that continuity property, which is a topological property of phi, on that measure mu, which is a limit. And if I don't know the limit well, it might be hard to check. Before we go into the proof, recall the formal definition of the push forward, which I just gave in that drawing here. This is the definition. The push forward mu phi, I think it works better, also written like this, is defined to be the measure of A by taking pre-images of sets A here to here, and that's where we use the measurability of phi. You can go back to stochastic ions, was one of the first examples in the measurability chapter. So now the proof. We first give the easy proof for the continuous case, and that's mostly what we are going to need. It's very simple in the continuous case, just using the transformation formula. So how do we prove it? Well, what we need to show is the convergence of those integrals to the limiting integral for all continuous and bounded test functions f. So we just need to be careful. F is a function which maps from be careful. Yes, from E2 to R. It must be defined on the space on which the measure is defined, which is E2 for this. So this is E2. And then this is E1. This is E1. And this is E2. So all we use is the transformation theorem here and here. and the weak convergence of the measures mu n on the space E1. So now how do we use the continuity? If phi maps E1 to E2 continuously, and we have a mapping F from E2 to R, which is also continuous, then the concatenation of both is a continuous function on E1. So we are allowed to use the definition of the weak convergence of the sequence mu1 on E1. That's it, nothing else. So continuous mapping is transformation formula. Okay, now we want to get rid of the continuity assumption and give the proof of the general theorem. So we need a bit of topology. First a claim, which, well, we should have proved before giving the theorem. This is a topological statement. So we are, this one, oh, sorry, that's a set defined from topology only. This is a measure. So we need to go from this topologically defined set to measurability. So we should prove this is a measurable set, otherwise that probability is not defined. Okay, so this should be measurable only for the theorem to make sense. So let's just prove it. So claim is the set, we call it U phi, of discontinuities, is Borel measurable. And we show this by showing this is an intersection union of open sets. Since open sets are measurable and unions and intersections, countable ones, are measurable again, this is measurable. And essentially what we do is just using the definition of continuity and the negation. Keep in mind, what does it mean, continuity? For all epsilon, there's a delta. So if I take a delta ball around X, the image of the delta ball is in the epsilon ball around phi of X. Analysis 2. So the negation is there is some epsilon, so that for all delta balls around X, the image is not in the delta ball around phi of X. Okay, so we can write this with unions and intersections as follows. We are replacing epsilon and deltas by 1 over n's. Yeah. We can always do this because if I have a small epsilon, I have an even smaller 1 over n. So we can write this event, the negation of what I just said, as unions of intersections of E and M's. And E and M's are these sets here, which is exactly the negation of what we want in the continuity. Here it's written, there are 2 points from a small ball around X, which are not mapped to the small ball around phi of X. And this is now the role of our epsilon. There is some epsilon, that's why there's a union here. So that for all balls, that's why the intersection around all balls, the ball is not mapped to the other ball. Okay, so we can write it like this. I think we did exactly the same somewhere in analysis 2 as well. So now we need, this is open. I leave this to you. This is just playing with the definition. You take a point X from one of those sets, and you need to show there's a ball around this. And you get this immediately from the triangle inequality. So they are open, so it's an intersection or a union of open sets. They are all Borel measurable, so it's Borel measurable. So that's the first point. Discontinuities of functions are Borel measurable. So the main proof now is rather easy. There's just a topological argument that I'm giving afterwards. So we're going to check Portmanteau. For Portmanteau, we need a closed set on the set, on the metric space, on which our target sequence lives, the sequence we're interested in. So we're interested in that sequence of the push forwards. So we are on the space E2. So let's take a closed set in E2. And now we argue as follows. So we're interested in the lim sub of that push forward sequence of F, the measure of F. And this is supposed to be smaller than the push forward of that set F. That's where we want to go. And if we proved this, then we proved property 3 of Portmanteau, and we have weak convergence. Okay, so what do we do?
So we don't know anything about phi, or not much about phi. We don't know this is closed. So what we do is, in order to get to something closed, we increase the probabilities by monotonicity of measures. By increasing that set, we take the closure. The closure is larger and it's closed. So it's larger. This is can be larger or equal to. Okay. So now this sequence here is weakly convergent, and this is closed. So by Portmanteau applied not to the push forward, but to the original sequence, which we know converges, we know that lim sub is smaller or equal to this measure, the limit measure of that closed set. Okay, so now if we could prove this measure is smaller or equal to this measure, which by definition is just a push forward of mu under phi of the set F, then we're done. Okay, so what we need to show is this. So how do we show this is true? We show this is true by showing that this holds. So if we have this inequality, which we are going to verify, this is a topological argument, then by subadditivity, we know mu of that guy is smaller or equal to mu of this plus mu of this. That's subadditivity. But by assumption, this one has zero measure. So that disappears. So we know mu of that guy is smaller or equal to mu of that guy. Well, since this is larger than this, it's actually even equal. So we get this is smaller or equal to by subadditivity, and actually, of course, also equal just by monotonicity for the other direction. No, that doesn't look pretty. Okay, so that's the proof. All we need to verify is star. I wrote it down here to combine it. This is just what I said. From the above, we proved this inequality for all closed sets, and by Portmanteau it's a convergence. So, star. We need to show this property. It looks frightening, but it's not frightening. We just need to recall what boundary points are. So we are interested in the boundary points of this set. So this is some set here, and this is a boundary point. So there are two good characterizations of boundary point in metric spaces. Either you say there's a sequence from the outside and a sequence from the inside, which converge to the point. Or you say, if you take any ball around the point, then the ball intersects the set and the complement. We have these two characterizations. We're going to use a second to show this subset relation. Okay, so first recall one of the possible formulations of continuity. This is the one I just stated in words 5 minutes ago. One of these characterizations is if you have a point x where the function is continuous, then, now I changed delta and epsilon, doesn't matter. For all delta positive, there's an epsilon positive, so that the small ball around x is mapped into a small ball around phi of x, and the small ball around phi of x has radius delta. So in mathematical terms, it's this one. So now we want to show this. So there are two cases. Well, first case, we take x from that set and assume phi is not continuous in x. Well, very good. This means x is in u phi, because these are the discontinuity points. Okay, that's it. If I assume it's not continuous, then x is in this, so it's in the union. So the interesting point, of course, is to take x, which is in that boundary, and phi is not continuous in x. Sorry, phi is continuous in x, so it's not in here. So then we need to show it's in here. So we need to show it's in the boundary of phi inverse, the preimage of the boundary of f. And we do it in this way. We need to construct such a ball around the point which intersects the set and the complement. Okay, so we take epsilon delta from above, from here. Okay, if we do this, then there is, because it's in here, there is where are we? There is a point in, this is now the small ball around X. There is a point in the intersection of a small ball around it and phi inverse of F. Yeah, because it should intersect phi inverse of X. At the same point, there's also a point in the intersection of that same ball with the complement of phi inverse of F. Yeah, so the first was saying there's a point here, and the other was saying there's a point there. Okay, that's because it's in the boundary. So now we use the continuity. So how do we use the continuity? Well, we say y is in B epsilon. So, but if y is in B epsilon, then because of this, phi of y is in B delta around phi of x. So this is written here. So first, since y is in the preimage of F, of course, phi of y is in F. And second, because it's in that ball, it's in the other ball. Phi of y is in the other ball. So same here. Since z is in the preimage of the complement, phi of z is in the complement. And secondly, since it's in here, it's in there. So what does it mean? Well, we have phi of y, and we have a ball around that guy, which intersects both F and F complement. So what we proved is that point must be in, that point phi of y must be in the boundary of F, but this means y itself was in the preimage of the boundary of F. It's a bit disgusting. These topology arguments are always a bit disgusting. So that's it. So if it's continuous, it's in here. So if it's discontinuous, it's in here. If it's continuous, it's in here. And all arguments are of that kind. So that's a proof. Continuous mapping. So now we're at the end of the lecture, and I only want to recall for you the relation of what we do here in abstract spaces to stochastic ions. So in stochastic ions, we discussed weak convergence. Let's just recall why. So just a reminder, this definition. So if I have a random variable with real values, then we defined the distribution of the random variables. Now we do the same. If I have a random variable on some probability space with values in some metric space, then we define exactly in the same way the distribution or the law of the random variable, which we call Px as in stochastic ions, as the push forward. So the measure Px of A is the probability our random variable takes values in A. And we write this in different ways. Formally, this is the probability of the omega and omega, so that x of omega is in omega, or it's the push forward measure. It can also be written as this. Sorry, Px. So we defined this in stochastic ions. We do exactly the same now. We say a random variable with values in metric spaces has a distribution, and the distribution is a measure on the metric space. And as in stochastic ions, the useful point about this is we don't need to know anything about this. The distribution of the random variable is on the target space. We completely forget about the original probability space, which can be anything. So now we define, just as in stochastic ions, a sequence of random variables with values in this metric space, which can be R, converges in distribution. Sometimes we also write this double arrow, or we say it converges weakly if the sequence of measures of distributions converges weakly, as defined before. Oh, there's an N too much. That's exactly the same as we know from stochastic ions. So now there's one important point. In stochastic ions, weak convergence was not defined through measures. It was defined through expectations. So let's recall why it's the same. In stochastic ions, this was the definition of weak convergence. As we said, a sequence of random variables converges in distribution or weakly to a limiting random variable if all these expectations converge. For bounded and continuous. Okay, so why it's the same? Well, the point is just these expectations are exactly the integrals we're talking about. Okay, so if the expectation is this integral, then this is just a definition, because the weak convergence of this one is now equivalent to the weak convergence of these measures, since this one is this one. So that's it. That's why weak convergence of measures is the same as convergence in distribution of random variables by the very definition. The point is just weak convergence of measures is more general. We can talk about convergence of finite measures, even of infinite measures. And for random variables, we only talk about probability measures. So what else did I want to mention? Yes. So the definition in stochastic ions of convergence in distribution was about convergence of expectations, yeah, which is the same as what we do now. There was a speciality in stochastic ions, and this cannot be generalized. This is a matter of the real numbers or of RD. You cannot generalize this to arbitrary metric spaces. So there was a theorem that we proved, and which is also used in stochastic 2, and sometimes it's used as a definition of the convergence in distribution. A sequence converges in distribution if and only if their distribution functions converge at the points of continuity of the limiting random variable. That might remind you of the Portmanteau Theorem. In the Portmanteau Theorem, we had that convergence on sets which have no mass for the limit. And if I think of intervals now, that continuity points are exactly the points where intervals have no mass. So boundaries of intervals have no mass. So this is actually the same as Portmanteau. So you prove it directly with Portmanteau with what I just mentioned. A continuity point means no mass at boundaries of intervals. So keep this in mind. We are going to use this next lecture in the proof of Powerhoof theorem, but this is really a real valued story. There's no analog to this. Essentially, it's telling us that in R, the weak convergence is determined by the convergence of the measures on intervals, but only for those interval points which have no mass in the limit. Okay. I want to finish the lecture with a very quick explanation about that, how was it called, continuous mapping theorem, if I translate everything into random variables. So if I translate everything from measures or the distribution of random variables into random variables itself, then the theorem, the continuous mapping theorem, tells us if I have a weakly converging sequence, and I apply a continuous function, then phi of that random variable, that sequence, converges to phi of the limit, if phi is continuous. Well, the simple proof that I gave you essentially was just saying, well, what do we need to do? You need to check, if you go into the definition of stochastic ions, that expectation of f applied to this converges. So expectation f of phi of xn converges to f of phi of x. But the main point is, well, if phi is continuous and f is continuous, then this again is a continuous function. So I can use the definition of the convergence in distribution for xn. And that's it. Okay, but the main point, so that's the simple point of continuous mapping. The main point is that we shouldn't forget, we don't need continuity. Now for this, according to the theorem, we only need that phi is continuous away from a null set of the distribution here. That's not very handleable. But as I said, in most of the cases, we're going to talk about continuous functions. So this relation of distribution convergence of random variables, real valued random variables, and distribution functions and weak convergence of the corresponding measures, something we're going to continue talking about next time.